Okay, we are going to add these vectors acting on a simple jib and tie crane. The lines that we see here are either drawn to scale or drawn to correct direction, or both. What we have here is the load that's suspended from the crane head, which is right here. So this is the load, is 20 kilonewtons. Because the scale that I have chosen is 1 centimeter equals 5 kilonewtons, this line is 4 centimeters long. The jib arm, which points in this direction here, is angled at 45 degrees to the horizontal or the vertical. Unfortunately, we do not know the size of the force in the jib arm. We just know that it points in this direction. The tie is angled at 35 degrees to the jib arm, which means the force in the tie points in this direction, but again, we don't know the size of that force. So that's the thing that we're going to try and work out, the size of the two mystery forces. And we're going to do that using a technique called the parallelogram method. So in the parallelogram method, we are going to take a vector and shift its location to some other place. And we're going to take another vector and shift its location to another place. And we're going to create, in effect, a tip-to-tail diagram, and if the conditions are right, a parallelogram. What I'm going to do to move the vectors is I'm going to draw a line of action that runs through this force, and then I line up on that line of action a straight edge from a right-angled triangle. I'm going to brace the other leg of that right-angled triangle with a ruler, and I'll hold that ruler into place, and now I can slide the triangle this way or this way and be assured that this line is parallel to the line of action. So what I will do now is I will slide it so the edge of the triangle touches the known vector. And I'm going to sketch in a line of action right here. So the line that I've just drawn is parallel to my original line of action. So this means I have a force which points down here, and I have another force which points up in this direction. Unfortunately, at this stage I still don't know how big that force is, so I can't decide how long that line should be. The piece that's over here is not necessarily all that important to us. Now what I'm going to do is I know that the forces acting on the crane head here are in equilibrium, which means they all add up to 0. So the force of the tie would start over here on this line of action and bring itself back over here to the crane head. So in fact, all I need to do is extend the line of action back until it intersects the jib force line of action right here. So that line, and now this line, are scaled force vectors. This is the force of the jib, the jib, and this is the force of the tie. So I can take out my ruler now and measure the length of each line and use the scale to determine the size of the force. So if I line this up here, measure this line, and this line is approximately 7 centimeters long, and because my scale is 1 centimeter equals 5 kilonewtons, so I multiply the 7 by 5 and I get the size of the force. So the force of the jib is 7 centimeters times 5 kilonewton per centimeter, which is 35 kilonewtons. And likewise, I can do the same thing here for the force of the tie. And I measure that line, and that line is more or less 5 centimeters long. 5 times 5 is 25. So the force of the tie is 25 kilonewtons. And there it is, the problem is done.